Okay, good morning, everyone. Haven't seen you in a week. I hope you're all well. I hope you all enjoyed the guest lecture by my PhD student, Caitlin Grasso, last Tuesday. Hope she gave you a good sense of what kind of PhD work goes on here at UVM. Obviously, in her case, she's working on evolving neural network-based cellular automata. It's not too far from what you're doing in this class, where instead of evolving neural network controlled cellular automata, you will eventually be evolving neural network controlled robots. Hopefully, Caitlin also gave you a good sense of what it's like to be a PhD student and what goes into making a decision about whether to carry on with graduate school or head into industry. Let's see. You're on to assignment 6 now, which is neurons. So we're getting very close to closing the loop that goes from motor neurons to motors to joints. Joints apply forces to links. The physics engine updates the positions and orientation of links, which causes changes in the touch sensor values, and those changed touch sensor values cause changes in sensor neuron values. But we have a bit of a gap still between sensor neuron and motor neuron values, which you're implementing this week. Next week in assignment 7, as you can probably guess, you're going to be adding in synapses that connect sensor neurons to motor neurons, and you'll now have closed loop control. Changes in action cause changes in relationship of the robot relative to its environment, which cause changes to the sensors, which cause changes to the motors, and around and around and around we go. Any questions about assignment 6? Any of the assignments? Anything else? Everyone's good? Speak now, forever hold your peace. All good? Okay. All right, so back to lecture. We've been working our way through the relatively short history of evolutionary robotics. Evolutionary robotics hasn't been around very long. We looked at some of the first 2 experiments. And then last time we started in this sort of sub-theme, which has 3 lectures in it, the sub-theme on minimal cognition. The idea here, this is one approach to understanding intelligence, which is to try and pare down the complexity of the agent, what we're asking it to do, pare down the complexity of the environment. So everything is minimal, with arguably an exception, which is the brain of these minimal agents. As we saw last time, these agents are going to be controlled by a particular kind of neural network called continuous time recurrent neural network. You remember there's a lot that goes into these, but the basic idea is we want to have neurons that are continuously changing values over time. We don't want discrete changes in value. Ultimately, for robots and organisms that detect the real world and have to grapple with the real world in real time, all of our sense organs, all of biological organisms' sense organs are continuous. The world is continuous. It's not broken up into discrete chunks like a physics engine is. So a CTRNN is a little bit more biologically realistic than the simpler neural networks we talked about towards the beginning of the class. Any questions about CTRNNs before we dive in and look at some of these minimally cognitive agents in lecture 9? No? Okay. All right, so what are we going to do in this lecture? In this lecture, we're actually going to look at 4 separate experiments that are drawn from this paper. This paper is a little bit old at this point, 21 years, but there's some really great ideas in here. You can think about this paper as sort of the Olympics. We're going to look at a series of events. Each event or each experiment is meant to evolve an agent that exhibits one of the building blocks of intelligence. You remember when we talked about the history and philosophy of AI, it's notoriously difficult to actually sit down and describe what we mean by intelligence. But what we can do is often come up with a good description, a formal description of the building blocks of intelligence. So we could try and evolve or otherwise train agents or robots to exhibit more and more of these building blocks. We're going to start the first of the 4 events or experiments we're going to look at today are agents which are able to perceive affordances in their environments. For those of you that have taken my human-computer interaction class, you should recognize this term affordances. Affordances is an idea that comes from psychology. And the idea here is that when an organism, or in our case, a robot, perceives its environment, it is not recognizing objects in the environment based on their geometrical properties. Instead, agents are looking at objects and reasoning about those objects based on what they, the observer, would be able to do with that object. So I've got 4 pictures here. You should probably be able to see there's something common among these 5 images. If I were to ask you what these 5 images are, you might say in chat, what's the common object in these 5 images? Start you off with an easy question. These are all chairs, right? It seems kind of an odd question for me to ask. Ben says it's a seat. Interesting, a little different. If I were to ask you to give me a description of a chair, some of you might give me back a geometric description. It's something that has a flat surface, and under that flat surface are 3 or 4 vertical uprights, known as legs of the chair. There's usually some sort of back or straight edge on the back. I picked these 5 images of these 5 chairs because whatever geometric description you give me of a chair is probably going to be violated by one or more of the chairs in these images. One of the things that slowed down computer graphics and machine learning in general for a long time was thinking that agents or organisms make sense of their world by looking at those objects and trying to describe them visually based on their geometric properties. Some of you, if I asked you what a chair is, you might use verbs instead. Chairs are things that are good for sitting. They can hold an adult human's weight. You put your bum on one part of it and you don't fall down. You could give me some description like that, which is really what an affordance is. So an affordance you can think of, affordance is a noun. You can think of an affordance as an advertisement. Imagine objects that are talking or sending advertisements out into the world to potential observers saying, you can sit on me, I can support your weight, I afford the action of sitting. One of the important things about affordance, and you can probably tell from the description of affordance here, this is a very powerful concept of embodied cognition, because it suggests that the way we make sense of the world is not by just looking at it, but by reasoning about, or by connecting what we see with us as individuals. Depending on how old you are or how big you are, whether you are abled or physically challenged, some of these objects might not actually register as chairs for you. So whether these are chairs depends very much on the individual observer who's observing them and the potential actions that that object might afford to the observer. Okay. So that's affordances, which comes from psychology. Let's see if we can try and get an agent to be able to perceive affordances for itself, not for humans, but for itself. Sorry, here's another, just before we move on. Here's another set of images which project a different affordance. And as you can see, these 2 sets of images have one image in common. So of course, any one object that we observe in the world is not projecting any one affordance, but multiple affordances. And which affordance seems most obvious to us, whichever advertisement we see, so to speak, depends on what else is going on in the world. So an affordance is not just dependent on the individual observer and potential actions, but a wider cloud of context or goals maybe that the agent has. What is the affordance that these 4 objects advertise? Previous set of images was a little bit easier. There was a common object. It's not so much a common object here. So Sid says fuel. energy, right? They afford or they provide energy for us, for humans, the observers, right? The action here might be warming ourselves or heating our homes or something like that, right? Okay. As you make your way around your world today and you observe the thousands of objects that are gonna pass in and out of your visual field today, think about all the advertisements that those objects are projecting to you. Okay. All right. So let's have a look at our first minimal agent. You can see it's pretty minimal. It's a two-dimensional square. It is trapped at the bottom of its screen, and like the old video game Space Invaders, the only thing that our hero can do here is move left and right along the bottom of the screen. So this robot has two motors. These motors are not attached to wheels like in the case of the Bratenberg vehicles. You can think about these two motor neurons as rockets. The left one can provide thrust in this direction, which causes the robot to move right, and the other rocket provides thrust to the right, causing the robot to move left. So it's got two opposing rockets, and the strength of the push of both of the strength of the thrust of those two rockets is going to determine how fast or how slowly it moves to the left and the right. Like we've seen before, this robot has 7 proximity sensors represented by the 7 gray line segments you see here that are emanating towards the top of the screen. As this minimal agent is moving left and right along the bottom of the screen, we are going to drop a pair of black objects. Those objects maintain the same distance. You can imagine that these objects are connected together, but there is a gap between them. You can see at this moment in time, the robot sees these pair of black objects because 3 of its 7 proximity sensors are the rays emanating there are broken. So the time of flight to go out and come back for a signal from that sensor has been reduced. So at every moment in time, the CTRNN, this neural network, is controlled by a continuous time recurrent neural network. At every moment in time, the CTRNN is receiving 7 floating point numbers from the outside world. And those numbers are moving through the CTRNN and ultimately sending out 2 floating point values, which control the strength of the 2 rockets. Okay, that's the sensors, motors, and CTRNN of the robot and some objects. These objects are falling, and as you can see, they have a gap between them. The fitness function for this robot is over here, which we'll talk about in a moment. The idea here is that if the gap between the objects is wider than the agent should move so that when the 2 objects hit the bottom of the screen, the agent is within the gap. It's not touching either of the 2 blocks. If the gap between the blocks is too narrow for the robot to get through, the agent should move far to the left or far to the right and not be anywhere near this pair of objects when those objects get to the ground. What is the affordance projected to this agent by this pair of black squares? A good way to summarize an affordance is to think of it as an adverb. So if we go back here, it's warmability. These objects warm us, or sit ability, or they're sittable, if you like. What is the affordance that this pair of objects presents to our agent at the bottom? Avoidance is a noun. In some cases, the agent should avoid the pair of blocks, but in other cases, the agent should move directly underneath the falling pair and let either block fall on either side of it. Not quite. It's not strictly avoidance. If the gap is broad enough and the robot runs away, that's a bad thing for it to do. So the agent should sit between the pair of blocks if the gap is wide enough, and the agent should run away from the pair of blocks if the gap is too narrow. Killability, that's an interesting one. Direction. Something about the gap. I think Alex is the closest here. Passability. Is the gap passable or threadable? Something like that, right? That's what as the agent moves underneath and it's going to brush these virtual whiskers across the underside of the pair of objects, it's trying to determine whether that gap is passable or not. If it's too narrow, run away. If it's broad enough, get between them and let either object fall on either side. I think passability is a good description of the affordance here. Okay, so what are we going to do? We're going to evolve these CTRNNs, and I won't bring up the slide deck again, but you'll remember that this robot has a bunch of neurons inside. Each neuron is described by a differential equation. Each of those differential equations has a series of parameters associated with it. Each neuron has its own tau, it has its own gain, it has its own bias, and I'm probably missing one. It also has a set of weights, which are all of the weights of the synapses that are arriving at that neuron. So we're going to evolve all of those parameters. To do so, we're going to create an evolutionary algorithm that has a population of CTRNNs. Each CTRNN is a set of ordinary differential equations. We're going to take each CTRNN, one in turn, and drop it into the agent and see how well it does at detecting the passability of these blocks. We're going to evaluate the fitness of the agent using each CTRNN in the population. CTRNNs that do not cause the robot to do what we want it to do, run away from narrow gapped objects and get between widely gapped objects. Those CTRNNs are deleted. We're going to make randomly modified copies of the CTRNNs that survive and continue this evolutionary process. Okay. How do we measure whether the robot is doing a good job of detecting passability or not? We're going to actually take each CTRNN in the population and drop it into the agent num trials times. We're going to evaluate each agent multiple times. In each of these trials, we're going to drop pairs of objects that are further or closer together. And we're going to drop them from different horizontal positions at the top of the screen. And you can see that the fitness here is a sum of P sub I, its performance during the ith trial, divided by the number of trials. So we're going to measure the average fitness, or how well on average does the agent do with this CTRNN over num trials times. So far, so good? If you have any questions, just drop them into chat. Otherwise, I'll carry on. Okay, so let's have a look at P sub I. There are two equations for P sub I. We're going to use the first one if the opening is too narrow. So what happens if we drop an object pair where the gap is too narrow for the agent to get between? What do we mean by too narrow? The distance between the pair of blocks here is narrower than the width of the agent. Okay, so we can see that P sub I can be set to 100 if the agent does not collide with the wall. So if the agent runs away and the gap is too narrow, we give it maximum points, 100 points. If the gap is too narrow and the agent collides with the wall, we're going to give it this many points, where D sub I is the distance between the agent and the object pair when the object pair hits the ground. So D sub I is the horizontal distance between them. We can see that if D sub I is 0, that means the agent is directly below or was hit head-on by the object pair, and that object pair had a narrow gap. The robot did the maximally wrong thing. Yeah. So the worst value of P sub I the agent can get is 0. It gets hit by the object. The best thing it can do is run away and get 100 points. If the object pair that's falling from the top of the screen has a wide enough aperture for the agent to get between, we're going to use this equation. It turns out there's an error in this equation in the paper, so I've corrected it for you here. So again, let's have a look at the 100 points here, which corresponds to the best thing the agent can do. It gets 100 points if the agent is between the blocks. If the gap is wide enough and the agent threads between the objects when the objects hit the ground, great. If the agent runs away when the aperture is wide enough, it gets the worst score, which is 100. If it's somewhere in between, if the agent doesn't run away and it doesn't try and get in the center but gets hit by one of the two walls or one of the two objects that are falling, it gets this many points. We have the d sub I now in a subtractive term. So remember, d sub I is the horizontal distance between the agent and the object pair when it hits the ground. So the greater the distance, the agent gets hit. If it's further away but still gets hit by the object pair, so maybe it got just grazed by the outside of the right-hand wall, for example, then we're subtracting a large value. This value is getting close to 0. As d sub I decreases, the agent is getting closer and closer to the center but still getting hit by the objects. We're giving it a little more points. We're subtracting less off. So this term here gives a little bit more reward for the agent to get towards the center, and then boom, suddenly it gets 100 points if it manages to get so far in the center that it's not hit by either object on either side. Okay, so we're going to use these two equations. We're going to drop different pairs of objects and compute the average fitness of the agent. We're going to evolve CTRNNs, and hopefully at the end of the evolutionary algorithm, we have one evolved CTRNN that if we drop it into the agent, and we drop pairs of objects with narrower or wider gaps, the agent does what it's supposed to do. The agent doesn't say to us passable, non-passable. The agent shows us, instead of telling us, it shows us that it understands the passability of these objects by its actions. If it gets underneath the object pair and stays there, that's the agent telling us, I think the gap is passable. If the agent gets underneath the object pair and then runs away, that's the agent telling us, I don't think the gap is passable. Okay, let's have a look and see how it actually did. What we're looking at here, this is a graph that shows us visually how well the final evolved CTRNN does. The CTRNN at the end of evolution that got the highest fitness. If we put that evolved CTRNN back into the agent after evolution has finished, and we drop a whole bunch of different object pairs, some of them have a narrower aperture width than the width of the agent. So minus numbers here represent, it doesn't indicate whether the length scale in this image is meters or centimeters or millimeters. Doesn't really matter. You can think of -2 as -2 length units. So this could be the gap is 2 centimeters narrower than the width of the agent, 4 centimeters narrower, doesn't matter. The right half of this figure corresponds to object pairs that were dropped where the aperture was passable. The width was 2 centimeters wider than the width of the agent, 4 centimeters wider than the agent, and so on. We did this a whole bunch of times, and each dot here, each point represents the average behavior of that agent when we dropped pairs of objects with that width. So we can drop, in this case, they dropped the same aperture width object pair from different horizontal positions at the top of the screen. And what did the agent do on average? What can you tell me about the left side of this figure? What did the agent do most of the time when the width was too narrow for it to pass through? If you have an idea, go ahead and type it into chat. The vertical axis here is showing the final horizontal separation between the agent and the object pair when the object pair hit the ground. As Ben says, it moved far away. It moved 40 centimeters away from the object pair. This axis doesn't tell us whether on average it moved 40 centimeters to the left or 40 centimeters to the right. It just got, as Ben says, far away. What does the agent, tell me about the right-hand side of this figure now. What does the agent do on average when the aperture is passable? If you have an idea, go ahead and type it into chat. It doesn't move very much. It actually moves quite a bit. Remember, we're dropping object pairs at different horizontal positions at the top of the screen. So in many cases, it needs to move. And as Ethan says, it gets right in between. So when the object pair hits the ground, the agent is about, on average, a little more than 0 horizontal distance away from the center point of the object pair. But that's not always true. You'll notice when the aperture width is, whatever that is, the aperture width is just a little bit wider than the width of the agent. What does the agent do? For those that haven't seen this before, go ahead and type an idea into chat if you have one. For those of you that haven't seen this before, these bars here, these are known as error bars. I'll just type this into chat here. And if you take a statistics class, you'll usually come across error bars. It says that on average, this is what the agent did, where this dot is. But sometimes it did this, and sometimes it did this. So the agent could do anything in this range, according to the vertical axis. But on average, it did this. What is the agent doing when the aperture is just barely passable? It's just the width of the gap is just a little bit broader than the width of the agent. In theory, it can always get between. In this case, the aperture is 0.2 centimeters wider than the width of the agent. What is it doing? It's running away. The average is 20 centimeters. Sometimes up here, it runs away very far. It runs 40 centimeters away. Sometimes it actually tries to thread the gap, right? So this agent evolved to not just recognize the affordance of passability. It's evolved the ability to be cautious. When the gap is a little bit wider, most of the time run away. You'll notice when the gap is just passable at 0, most of the time the agent runs away, right? So I forget what that expression is. Cowardice is the better side of valor or something like that, right? If you're not quite sure, run away. Pretty good strategy. Okay. Let's have a look at the two figures in the top left now. This shows us in a little more detail. What the agent is actually doing. So again, we're looking at one evolved CTRNN. We're going to take a pair. Of objects in this panel here. We're going to put the object at -40 horizontal position, which means the agent is sitting bottom center of the screen, and we're going to place the object pair. Up here, 40 centimeters to the left of the agent, and then that pair is going to start dropping. The aperture is too narrow in this case. We're going to then move over here, put the object pair here, drop that, move the object pair over here, drop, 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 until we get to here. We're going to put the object pair 40 centimeters to the right of the agent at the top of the screen and let that pair start to fall. So each of the black trajectories here represents the horizontal position between the agent and the object pair as it's falling. I think I forgot to say this at the beginning. The object pair always falls directly straight down. It's the agent that's moving. So when horizontal position changes, that means the agent is moving at the bottom of the screen. What can you tell me about what the agent does when we drop non-passable object pairs from the top of the screen at these different positions? This figure now gives us a little more detail about what the agent is doing. We now have vertical position on the vertical axis. So this is the vertical height, if you like, the vertical position of the object pair, which is obviously decreasing as the object pair falls. What is the agent doing? Does the agent always do the same thing, or does it do different things? Alex says the agent moves to the opposite side of the falling objects. It can be a little hard to follow this. They should have drawn this with different colors, I think. But you'll notice when objects are dropped top left relative to the agent, these all converge and come down here and end up over here, which means as these objects were falling, the agent got underneath them, and then it carried on over here, and the agent and the object pair landed down here. Okay. Let's take the exact same CTRN and drop it back into the agent multiple times. And we're going to drop the object pair from different horizontal positions at the top of the screen again, but now the gap is passable. What does the agent do in this case? Same CTRN, but we have different environments. It passes through, right? So you'll notice that by the time that the object pair is 40 centimeters above the agent gets directly underneath that pair and doesn't move and lets either object fall on either side of it. Okay. If we take these two pictures and compare them, at what point in time does the agent make a decision? This is another important building block of intelligence, is decision making. At various points in our lives, we need to decide A or B. We can't have both. At what point does the agent recognize or detect the passability of the gap and make a decision about what to do? Lucas says like 4/7 of the way down. That sounds about reasonable. You'll notice that when the objects are 50 units or above, it looks like the agent is doing more or less the same thing in all these situations, regardless of whether the gap is passable or not. The agent moves more or less in the same way. But after a height of 50, so after the object pair is below a height of 50 centimeters, the agent seems to do different things. It seems very suggestive that the agent makes a decision at height when the object pair is at a height of 50 centimeters. It decides, is the object pair passable or not, and acts accordingly. If you've been paying attention in this class, and you can probably tell from the way I'm speaking that that may not be the case. Thinking about thinking is misleading. We don't know where in the CTRN a decision is made to move or not move. I bet it would be very difficult to dissect this evolved CTRN and point at a particular neuron as the neuron that makes the decision about whether to stay or flee. Remember when we looked at the evolved neural network for the gantry robot that distinguished between triangles and rectangles? There was no triangle detector or rectangle detector. The agent acts as if it's made a decision at this point in time, but it's hard to say. Okay. The last analysis we'll do on this particular event before moving on to a next one is now we're going to take the same CTRN again, and we're going to expose it to a very large number of environments that it never saw during evolution. We're going to drop the object pair at the top of the screen again at different initial horizontal positions at the top of the screen, like we did before. And we are also going to drop object pairs that have a large number of relative aperture widths. The lower half of this figure corresponds to widths that are impassable, or gaps that are impassable. The top half of this figure corresponds to gaps that are passable. So you'll notice that there's a series of pixels here. So each pixel has a horizontal and a vertical coordinate. The horizontal coordinate represents, each pixel corresponds to a different trial with this evolved CTRN. That pixel has two coordinates. What was the initial horizontal position of the object pair? And the vertical coordinate represents what was the relative aperture width of that object pair. And then depending on what the agent does, we're going to color that pixel white, gray, or black. We're going to paint that pixel white if the agent did what it was supposed to do. It ran away if the gap was impassable and stayed between the pair of objects if the gap was passable. We're going to paint a pixel as black if the agent did the wrong thing. It ran away from passable gaps and tried to thread between impassable gaps. That we're going to paint those pixels black. And if it hit either of the two objects, so it neither ran away nor managed to get between the object pair, we're going to paint that pixel gray. What can you tell me about the bottom half here? How did the agent do on average when it was presented with a large number of environments or a large number of object pairs that it had never actually seen during evolution? What does this unbroken field of white pixels in the bottom half of the image tell us about the agent? The agent always avoids impassable objects. Lucas says the agent did well. Right, exactly. The top half, not so much. The agent made quite a few mistakes when the relative aperture width was wide enough. Good job, agent. Exactly. You'll notice when the width was just barely passable, which is all the pixels that are just above the horizontal midpoint here, there's a lot of black. The agent ran away when it could, in theory, have gotten between the object pairs. You'll notice there's also a lot of gray out here, and there is a long spike of black up here. When the object pair was dropped directly above the agent, even when the gap was almost 3 centimeters wider than the agent ran away. Seems strange. Anyone have an idea about why the agent is making so many obvious mistakes in this situation? This is tricky to figure out. Any ideas? Missy says, does the spike in the middle have to do with the gap between close enough to the air level in the sensors? Not in this case. Remember, the agent is moving back and forth, and it is brushing these virtual whiskers underneath the undersides of the object pair. The object pair is falling directly above the agent, and the agent can definitely see this object pair, can definitely sense the gap between the objects, and it runs away. What is going on here? These obvious errors, when the gap is much, much wider than the agent, does it run away? That's only happening when the object pair is placed directly above the agent. Remember, this is a wide range of environments that the robot did not see during evolution. Any ideas? It's kind of tricky to see in this case. Maybe a problem with the activation function? Maybe, but the activation function is operating in all these other conditions as well. There's a hint actually up here. And I didn't explicitly mention this, so it would be hard to figure this out. During evolution, they dropped the object pair from all of these positions, and you'll notice there's a little bit of a gap here. For some reason, when they coded up this experiment, the number of trials that were performed during evolution, they never actually dropped the object pair directly above the agent. So the agent has seen objects far above it top left, top right, but not directly above. So this region in here corresponds to situations that the agent, that were very different from anything the agent ever saw. Down here, the agent is directly underneath the object pair. The horizontal position is 0, but the object pair is also much closer to the agent. The agent has never seen object pairs that are directly above it at the top of the screen. This is an important reminder about evolutionary robotics and AI in general. We can train our agents or our robots in lots of different situations, but it is likely that there are always going to be situations in reality, once we deploy our autonomous vehicles or our drones or whatever it is that we've developed, when we deploy it out into the world, there are situations that are going to arrive that agent never experienced during training. And it is difficult or impossible for us. Actually, no one knows yet how to provide a proof that even in situations the agents have never seen before, that the agent will do the right thing. Sid here mentions edge case scenarios, right? So an edge case is engineering lingo for situations that are conceptually on the edge. They're just beyond or at the edge of what the agent has experienced. This, I would argue, is the biggest challenge to wide-scale deployment of autonomous vehicles, drones, autonomous planes, automated control of energy power stations in the electric grid. We cannot make a lot of good progress on automating national infrastructure because of this, because of the uncertainty of what AI agents will do in situations they haven't, quote unquote, seen before. Okay, back to minimal cognition. Let's move on to our second event. This one is something we've talked about already, which one of the first things that human agents, babies, have to do when they're born is figure out where I end and where the world begins, right? Discriminating between self and non-self. We saw a robot learn to do this. Which robot was it? Anybody remember? We've talked about an agent, we talked about a robot that was able to learn how to discriminate between self and non-self. Cog, exactly, right? Or BabyBot. Actually, both Cog and BabyBot could do it. Okay, here's a minimal version of this experiment. We're going to put an agent at the bottom of the screen again. In this case, it is not able to move left and right. Instead, this agent has an arm and a hand, the little circular hand in front of it, and it can rotate that arm in front of it. We're going to keep restricted to the two-dimensional plane. It can rotate that arm in front of itself, and as it does, its hand occludes its vision. You'll notice that, again, we have this agent has 7 proximity sensors. At this point in time, it's actually 1, 2, no, it is 2, there's 2. 1, 2, 3, 4, 5, 6, 7. The arm is blocking the second and third proximity sensor in this case, but there is also a falling object up here, which is falling down, but falling in this direction, that's blocking the 7th proximity sensor. So this agent at this moment in time is simultaneously seeing self and non-self. Okay. What does this agent have to do? All of these objects are going to be dropped from different horizontal positions at the top of the screen. They're all going to fall with different angles, but all of them are going to hit somewhere on this dashed semicircle, which you can think of as sort of basically the object's body. So what the agent needs to do is figure out where the object is going to hit on this semicircle, and it has to move its hand to that position or that angle at the moment that that object hits the semicircle, and that's going to count as the object grabbing or catching the object. Okay, so in order to know where the object is, where it's moving, and when and where it's going to hit the agent needs to be able to discriminate between self and non-self. In most of the time steps here, this agent is going to be able to simultaneously see self and non-self. We're going to do the same thing we did before. We're going to evolve a population of CTRNNs. We're going to take each CTRNN and drop it into this agent num trials number of times. In each of those trials, in the ith trial, we're going to compute P sub I, which is the performance of the agent during the ith trial using the current CTRNN. What is P sub I? Again, there's an error in the paper here. I've corrected it for you. We are going to try and minimize theta sub I, and theta sub I is the angular error at the end of the ith trial. The ith trial ends when the black circle hits the dashed semicircle here. When it does, that collision event has its own angle. Where on that semicircle did it hit? And we have another angle, which is the angle of the arm, and we take the difference between these two angles, and we want that difference or that error to be 0. We want the angle of the arm to be exactly the same as the angle of collision. Okay, so you'll notice there's one minus here, and there's a ratio. Alex asks the following question. Is the agent sensing the position of the hand through the vision sensors or by some other means? The former. The agent only sees its hand by its 7 vision sensors. So like this agent, both agents have only 7 sensor neurons that return 7 floating point values, the lengths of these beams. And there is, in this case, just one, there's just one motor neuron which controls the angle of the hand. That's all it sees. If we gave it an angle sensor so it can directly detect the angle of the hand, then discrimination between self and non-self is trivial. As this object becomes much closer, you can imagine that beams in this direction are very short and beams in this direction are very short. Which is self and which is non-self? The agent has to be able to evolve the ability to tell the difference. Okay. Make sense? Okay. All right, so performance is 1 minus some ratio. You'll notice here the ratio here, if the angular error is 0, then we have the minimum between pi over 4 and 0 is 0. 0 over pi over 4 is 0. 1 minus 0 is 1. So the best thing this agent can do, the maximum number of points it can get, is 1. And it gets the maximum number of points if the angular error is 0, if it manages to catch the object where it hits in front of the agent. If angular error is very large, greater than pi over 4, we take the minimum here, the minimum of pi over 4, and an error that's greater than pi over 4 is pi over 4. Pi over 4 divided by pi over 4 is 1. 1 minus 1 is 0. The worst thing the agent can do is, for example, if the object hits to the agent's left and its arm is all the way to the right, that angular error is big. The agent did the wrong thing. Make sense? Okay, so do the same thing we did before, evolution, 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 and at the end we take the evolved CTRNN that has the highest average P, that does the best over all the trials, and we then create this plot which shows us how this CTRNN causes the agent to behave. We're going to drop a whole bunch of these black circles. And all of these black circles are going to hit at minus pi over 8 or pi over 8. They're going to hit different positions or different angles in front of the agent. When it hits, we can plot the final angle of the arm. Again, negative being the arm is to the left of the agent's front, and positive angles are the arm is to the right of the agent. What does all of this information here tell you about how the agent is doing? While you're thinking about that, and if you have an idea, go ahead and type it into chat. Remember that the black circles here represent how well. Black circle represents what was the average angle of the arm when we dropped a whole bunch of objects and all of those objects hit at minus pi over whatever that is there, somewhere to the left. So in this case, we can drop black circles that have different angles, but imagine all those different angles hit at a particular angle. What is the average? What does the arm do on average? Remember the error bars here, these thin vertical lines, represent sort of the range of final arm angle. As Alex says, the arm angle matches the final object arm perfectly. Not quite perfectly. You'll notice behind all of the black material is a gray dashed line, which is the perfect diagonal. If the agent did perfectly, all of these black dots would be sitting exactly on this gray diagonal, and the error bars would disappear. The agent would do exactly the right thing in all of those conditions. It's not perfect, but it's pretty darn close. You'll notice some of the error bars are taller than at other places, representing the agent is doing more varied things. So here in the center, meaning we're dropping a whole bunch of objects at different positions. They're all falling, but they're all hitting directly above the agent. The agent's arm is sort of ends up in different positions, close to zero, but not quite. Okay, this is my favorite figure from this paper, but it is the trickiest one. It's going to take a little bit to digest this one, so bear with me here. We're going to drop. You'll notice there's a whole bunch. Let's start with the trajectories. There's a whole bunch of trajectories that have different shades of gray, and the shades of gray are shown up here. Light colored trajectories mean that the angular position of the object was to the agent's right. So remember, the agent is immobile. It sits transfixed at the bottom center of the screen. And light colored trajectories means the object was dropped pi over 8 radians above and to the right of the agent. Dark colored trajectories represent that the agent's down here. Now we're going to drop the object from minus pi over 8 radians, top left of the agent. And all the different colors or all the other grayscales are somewhere in between. So we're dropping objects from different horizontal positions at the top of the screen, but all of them are falling and they're eventually going to hit the agent right in front at 0. The agent is going to catch objects at the midline. So they all start at different horizontal positions, but they're all falling inward, and they're going to hit right in front of the agent. The curvature of the line, so the lines are snaking left and right. At any point in time, the horizontal position of a point on the trajectory represents the angle of the arm itself. So you'll notice half of the trajectories start over here and half the trajectories start over here. So in these half cases, we dragged the arm at the beginning of the trial to minus pi over 8 radians. In this half of the trials, we dragged the arm to plus pi over 8 radians, and then wherever the object was, we dropped that object. You'll notice that there are both light and dark trajectories emanating from over here. Tell me about the black trajectory or the dark trajectory that starts from top right. There's obviously multiple ones, but let's take one of these very dark trajectories that starts over here. What situation does that trajectory represent? We have a dark trajectory, and that trajectory started its descent from over here. What can you tell me about the object and the initial angle of the agent's arm in that situation. Takes a little bit to think through this one. Any ideas? The arm was on the right of pi over 8. The arm was on the right. So the arm is on the right. That's right. So over here, all of the trajectories that start on the right-hand side, we dragged the agent's arm to pi over 8 radians. So the arm was on the right of pi over 8. And the color of the trajectory is black or dark. What does that tell us? What does the color of the trajectory tell us? It's not about the arm. So Missy's got half of it right. We're thinking about a dark trajectory that starts from here. What can you tell me about the object in that case? The object is on the left, exactly. So a black trajectory that starts from here means we cranked the arm to the right, but the object fell from the left. A light trajectory that starts over here represents the fact that the trajectory is to the left means we cranked the arm to the left, but we dropped the object from the right. In all of these cases, remember the objects are falling and they're going to hit just to the center of the robot. What can you tell me about what the robot does in general in all of these cases? You'll notice that in most cases at the end, the position of the trajectories all end at more or less the midline. So the robot did more or less the right thing in these cases. The arm was at 0 when the object was at 0. What's happening? What can you tell me about the behavior of the robot in this case? So Missy says, what can we make of the asymmetry at the top left? The asymmetry in the top left. Missy, can you elaborate? You can unmute yourself if you like, if you want to expand on your question.
Yeah, this is a little off topic, but does that, so that trajectory that's sticking out to the left on the top, does that just mean that the arm never extended to the, I guess, is this something that results from the different positions the balls were dropped, or is it something that results from the action of the robot?
Yeah, I think I understand your question. So what I neglected to mention is you'll notice obviously that the horizontal position of these trajectories is changing over time. As the object is falling, the horizontal position of the trajectory is changing. What is that telling us? That's telling us the position of the arm. Remember that I mentioned that all of the trajectories that start left means the arm starts left, and all of the trajectories that start right means the arm started right. So the horizontal position of the trajectory is representing the horizontal angle of the arm. It says nothing about the current angle of the object. You'll notice that all of these trajectories end at an angle of 0, representing that in all these cases, the arm ended being perfectly vertically erect. And this is exactly where the object hits, right? The object is always hitting in the midline. So that's telling us that it caught the object in all of these cases. The asymmetry up here that you mentioned, the fact that the trajectory starts at minus pi over 8 and decreases, becomes more negative in this case. What is this telling you about the behavior of the agent? What is the agent doing in all of these situations? You'll notice there's some light colored trajectories, but there's some darker trajectories underneath. So in all these cases where the arm started at minus pi over 8, in some cases we dropped object top left, and so, which are the black trajectories. Some cases we dropped the object top right, which are the light trajectories. What did the robot do? As Missy mentions, the arm moved further to the left, moved its arm maybe in the wrong way. That's a great point. Is it wrong? Is the agent doing the wrong thing? Whenever we crank the arm to the left, the arm goes further to the left and then starts to come back again. It also does the same thing when we start with the arm initially cranked all the way to positive pi over 8. It also sweeps left and then starts to go back again. Is the agent doing the wrong thing? In theory, what should all of these trajectories look like? What is the theoretically optimal thing to do? I'm sorry, Ethan was the one that mentioned it moves its arm in the wrong way. Is it really moving its arm in the wrong way? Should be smooth, straight lines to the center. So maybe we would have straight trajectories all coming down here. That's possible. Maybe that's the best thing to do. The agent immediately detects or decides or recognizes, I'm putting quotations around all these things because we don't actually know what's going on inside the CTRNN, is that it gradually moves its arm to front center. You'll note that the theta sub i's here only have one subscript I, which is the ith trial. There's nothing in here about subscript t. There's nothing about time. There's nothing in the fitness function that says it should get its arm immediately to where the object is. It doesn't need to anticipate where the object is going to hit. It just needs to get its arm there beforehand. Whatever this arm is doing, it's waving like crazy most of the time and only stops waving right at the end. Is that the wrong thing to be doing, waving back and forth? Why might it be waving back and forth? I'll give you a hint. Remember when we were talking about Cog or BabyBot, who was also trying to learn the ability to distinguish between self and non-self? What was the information that it put together to figure out what was self and non-self? If you were to ask BabyBot, its eyes are not on the arm, its eyes are down here. Its eyes, if you like, are the 7 beams that are coming out. And some of those beams hit the hand, which is the small black circle here, and they occlude things. As Missy mentions here, maybe it's waving back and forth to assess the values of all of its sensors. One of the ways that BabyBot was able to distinguish between self and non-self was known as sensor. I'm not sure if I actually mentioned this. I'm not sure if I mentioned this when we talked about BabyBot, is sensor motor contingencies. So what do I mean by a contingency? A contingency is an if. If I send commands to my motors, then this happens. That's something that BabyBot used. That is actually a very good definition of self. I send commands to the muscles in my arm, and I see some blob that starts to move, that's moving in my visual field. When I stop sending commands to my motors, that blob stops moving. That's the definition of self. You can almost think of a sensor motor contingency as the affordance of self. This is now getting kind of deep into embodied cognition. This is a little bit beyond minimal cognition. One of the reasons, like Missy mentioned here, the intuition is probably that by waving its hand in front of its eyes, it's learning what is hand and what is the ball. The ball will keep breaking these beams, regardless of whether the robot moves its hand or not. But if it sends commands to its arm, different beams will be broken by the movement of the hand. Maybe by doing that, the agent is able to distinguish between hand and object. Once it can quote unquote focus on object, quote unquote figure out where object is going to hit and get its hand there. It's not clear whether we could evolve a CTRNN in which the agent holds still and watches the object and is able to determine where the object hits. Whatever solution it is, this is an active solution. If you watch a very young human child, they very rarely sit still. They are waving their hands, they're grabbing things, breaking things, hitting things, grabbing things, putting them in their mouths. They're generating a lot of sensor motor data as they explore their world. And one of the things babies are probably doing during that process is learning between self and non-self using sensor motor contingencies. All good? Okay. Okay, we got 10 minutes left. I think we can finish the third event, which is another building block of intelligence, which is very important, is memory. If you have an agent that can't remember anything, it's going to have a hard time exhibiting intelligent behavior. One of the best, I mentioned that it's very hard to define what intelligence is. The best definition that I've ever heard is to prevent your future self from getting stuck in corners. Or to say it even more simply, is to keep your options open. Intelligent humans and intelligent animals and intelligent robots make sure that they do things now that will give them more options in the future. In order to do that, that's known as prospection. That's thinking into the future. In order to prospect, you also need memory. What are the things that happened in the past and what worked and what didn't? Given that information that I remember, what is possible, what is likely to happen in future, and what are the things that I'm going to need to be able to do to handle those future scenarios that worked when I experienced those scenarios in the past? Okay, so that's just a sort of a defense of why memory is important for intelligent behavior. How are they going to evolve a robot that is able to remember things? Well, we're going to go back to our rocket-controlled agent. We've got our agent that now has two motor neurons. Those two motor neurons control two rockets that exert thrust, causing the agent to move left and right along the bottom of the screen. We're going to drop single objects from above, as before. Also, as before, this agent has 7 sensor neurons that are recording the 7 values arriving from the 7 proximity sensors. Those 7 floating point values are representing the length of these beams, right? So in all 3 cases we've seen so far, the agent has 7 values representing proximity. That's what it sees in its world. The twist here is that as these objects are falling, the moment that the agent starts moving, it goes blind. That's what these dashed lines are meant to represent. All of the sensors turn off the moment the agent starts moving. What that means is that the agent is going to have to figure out where the object is and which direction it's falling in and how fast is it falling before the agent starts moving. Once it has all that information, it should be able to combine it to figure out where along the bottom of the screen the object is going to hit, and it should move to get there and capture the object right when the object hits the ground. Okay. We're going to do the same thing we did before. We're going to perform a number of trials with the same CTRNN, and we're going to evolve populations of CTRNN so that on average, the agent is at where the object hits the bottom of the screen. Here's our fitness function here. This should say P sub I equals. They're taking the average over here. So we've got our number of trials here. So in each of the ith trials, we're going to compute D sub I, the horizontal distance between the object's final position, where did it hit, and the agent's final position. So you can see that the d sub i's are to the right of a minus sign. So we want to evolve agents that minimize this penalty term. The minus sign tells us that this term is a penalty term. We want to maximize this whole quantity. So d sub I should be as close to 0, should be as small as possible. An optimal agent is one that captures the object in each of the num trials cases, getting a d sub I equal to 0 in each of the num trials cases, and getting a maximum score of 200. 200 minus 0 is 200. Evolve, 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 evolve. At the end, they take the CTRNN that has the highest fitness and drop that CTRNN back into the agent under a large number of cases. What can you tell me about this evolve CTRNN? How well does it cause the agent to do at this task? We've got final object position. When you're trying to understand a scientific figure, always start with the axes. The horizontal axis shows the final object position. So where does the final object hit at the bottom of the screen? And on the vertical axis, we have the final agent position. Where is the agent sitting? What is the horizontal position of the agent at the bottom of the screen when the object hits the ground? What can you tell me about the average behavior of this agent? How's it doing? Logan says there's 3 areas of deviation from the perfect position being the dashed gray line underneath. As Logan says, the top, top, bottom, and the center. So when the object hits all the way to the bottom right of the screen, the agent doesn't quite get there. When the object hits 40 centimeters to the left over here, the agent also doesn't quite get there. When the objects hit directly center, bottom screen, the agent isn't always there either. In all the other cases, it did pretty well. As always, evolution gave us a pretty good solution, but not an optimal solution. Let's have a look, like we did before, in a little more detail. Let's analyze this single evolve CTRNN in a little more detail. We're going to play back this CTRNN in the agent 1, 2, 3, 4, 5, 6, 7, 8, 16 times. We're going to replay the CTRNN 16 times, where we start by dropping an object from the top of the screen. And these the starts of the trajectories are all vertical. The horizontal position down here is telling us in this case, horizontal position is the distance between the agent and the falling object. This should probably say horizontal error or distance or difference. I think that would have been a little more fair. This is a little confusing. You'll notice that all of these trajectories, I mentioned the objects start falling, the objects are all falling directly vertically in all of these 16 cases. The trajectories are vertical, and some of them stay vertical for longer than others. What can you conclude from this figure? What is the agent doing in these 16 cases? You'll notice at the end, when the vertical position of the object is 0, the horizontal difference or error, the horizontal distance between the agent and the object, which is now at the ground, is close to 0, almost 0. So the agent has captured the object in almost all of these cases, but not quite. What is the agent doing? How does the agent solve the problem in this case? Any ideas? Sorry, I didn't mention the colors of the trajectories. So the black trajectories, as you can see down here at the bottom, these are like successful cases. The agent grabbed the object in these cases. The gray trajectories means the agent sort of missed the object. The object hit a little bit to the left of the agent, or the object hit a little bit to the right of the agent. How is the agent solving this problem? Okay, I think we're out of time for today, so I will leave this one with you to mull over. Remember that you have a quiz due tonight. You're working on assignment 6, which is implementing neurons into your simulated robot. I hope you all have a good rest of the week and weekend, and I'll see you back here Tuesday morning. Thanks very much, everyone. Bye-bye.